Hi, Rashid here. Today we are going to talk about propagation delay and transition time. We have been talking about propagation delays, but today I'm going to focus on how we can reduce delay. And I'm not sure if I started talking about transition time, but we will same parameters that affect delay also affect transition time. So it's an important thing from the design perspective. This is if this is your input to um, this is your input to inverter and this is output. Inverter has PMOS and NMOS. So when the input rises, output falls. And this is the time when NMOS starts turning on. When its input is 1, output is 0. So this is really the delay from here to here. And as I mentioned, we can measure in spice if we have a waveform. We can measure from 50% point to the 50% point here. And that will be the high to low delay. High to low delay. Similarly, the rise part of the will be, we can measure from delay from here to here, and I intentionally created a little bit more delay here to show you that we can have a different sort of slopes of falling and going up. And here delay will be more because of this slow. I mean, it started a bit late. But this delay is our low to high delay. And during this time, PMOS turns on. So when NMOS turns on, if you remember, oops, I don't know what happened. Okay, when high to low, NMOS transistor turns on. So if you remember the equation I mentioned to you, again, in a waveform, we can always measure 50% delay here. You don't need an equation. And in physical design, that delay will come through standard cell library, and I will talk about that. So we will not be calculating this delay manually with or an equation. But equations, as I told you, equations are really helpful for you to understand dependencies. So delay, uh, this should be not 0 to 50%, but 50% to 50%. Let's fix that thing. And that is 50% here to here, and that's really the case when NMOS transistors turn on. So that's why I put R resistance on resistance of NMOS, and the SCL means the drain resistance. I should maybe mention here. So whenever I say C load, load is really the drain capacitance when there is no external wire there. So here I'm talking about only the intrinsic characteristics of NMOS or of transistor. So external wire is not connected. So and it's a continuity of my previous video. So if you're following previous video, you will see that what I'm talking about. For interconnect, I will talk later on. So again, the delay is 0.69 of on resistance for NMOS and the drain capacitance of NMOS. You're probably thinking, okay, what is 0.69? Again, I already explained how it came. So what we are assuming, in case you haven't watched video, or I'm not sure if I have explained it well, because it did add few things here. So if you remember, I'm assuming that from the output side, transistor acts like a resistance and a capacitance in series, and this one, and here in this case, think of just NMOS. So our output voltage over here is really the voltage across this capacitor. So think of this as a capacitor connected to ground, and the kind of effect of what is driving this is like a Thevenin equivalent is a voltage source, which is, we can assume, is like the same as input, because that is really the thing that is driving current here. And then there is an on resistance, which is part of the source. The source is not ideal, it will have some resistance to this one. So if you remember, I mentioned that if you solve equation for output voltage over here, it comes like this. This is the one. V out is equal to the VD, which is the maximum voltage level that output can have, which is the supply voltage here. Then 1 minus E to the power minus T over RC, and R is the on resistance of NMOS in case when this is on, and the C is really the capacitive load over here, which can be in this case the PMOS as well, but for this case I'm assuming this is NMOS capacitance, the drain capacitance, and we talk in detail what are the components of the C and what are the components of R. So I derived the question. You don't need to derive this, but you just need to remember, as I said, just remember that this thing that I said here, so we want to understand when V out. Do I have a waveform? Yes. When you apply a step voltage at input over here. I'm not sure if I'm repeating things that I mentioned already. I forgot, so but it's okay. So when you apply this voltage to the input of that above circuit, output voltage doesn't go like sharp like that step. It takes a little bit time. So what we really want to calculate in this case, and again this is a simplification of a real situation. Real situation will have a different delay, will not be step, and output will be further worse. But from this one, at least we can derive an equation, which helps us kind of approximate things. So what we really want to understand, when this waveform from 0 to 1 reaches 50% of its final value is VD, which is supply voltage, so 50% somewhere here. The time we really want to figure out, the time it needs for this signal to reach somewhere here, maybe, sorry, here, 50% of VDD. And that is really kind of a delay here. I know in the waveform I said 50% point here, but really this is our input in this case is really happening here, right? So in this case 0 to 50 is the same time that I was saying the real situation is 50. Sorry if I'm not making sense. So if this is your input and this is your, sorry, I'm just assuming there's no inversion happening. So this is the time, the delay. But in this our case, it's really this voltage is input is this and output is this. Okay, so 0 starts here and 50%. So it's the same thing I'm talking about. What is that time? So you can take a snapshot of this. That time is V out when it's 50% of VDD, when you put everything here and you solve for T. The time is 0.69 RC. Okay, and that's what I'm referring here. Let's take a, so that I don't have to come back here. Let's copy. Let's leave it here. So that, oops. Here, I was referring here, 0.69. So similarly, when it goes from low to high, when PMOS is on, then you will say the 0.69 of R on PMOS and C drain of PMOS, right? So, and let's touch the transition time before we get into this. Transition time is how long, look, you can look at this, the fall transition time. Transition, it makes a transition from here to here. Okay, what is the slope of this? What it says slope of this? You can see slope of this is much higher. It takes much longer. So the time it takes from 10%, 90% of the final value to 10% of the final value. like zero point 0.1 VDD and zero point 0.9 VDD, that difference is called transition time. So propagation delay is related to from input to output, okay, but transition time is just on the output from 90% point to 10%. Some people also define as 80 to 20. I've seen within static timing analysis or within libraries mostly around 80-20, but okay, it doesn't matter. 90-20, and here will also be same thing, 10% and 90%. So from 10 to 90, here is from 90 to 10. These are called transition times, slews, not skews, slews. This terminology is used in ST and physical design. Slew is same as transition times. So question is right now, how to how you can reduce the delay and transition time. So you can measure it or you can hand calculate using equations. And by the way, 10 to 90% is 2 point, I think it's 2.2. 2.2 of our on NMOS and CMOS. And how did I come up is 2. Oops, why is it's also here. When you calculate for V out to be 10% of VDD, you come up with this 0.1 RC. V out is 90% of VDD, you come about 2.3 RC. You take to subtract them, you come up with 2.2 RC. You can take a snapshot of this. Okay. All right, so that is that 2.2. And before I go into this, again, sorry, remember one thing, that on resistance of NMOS is much lower than the on resistance of PMOS. Again, PMOS offers more resistance to the flow of current compared to NMOS. In PMOS, what are the carriers? Holes in the channel I'm talking about. In NMOS, these are electrons. So the P material, the holes, the relative mobility is less than electrons. You might be thinking, okay, what is a hole? Hole is not actual thing; it's the movement of. But if you track the movement of holes relative to movement of electrons, I think they found it to be less. And for that reason, you typically try to improve the resistance. So what happens if PMOS has more resistance? It will have more transition time. You see here? So the transition time for PMOS is higher than NMOS. And that is when you leave it default, like the width and length of PMOS is exactly same as length. Remember the current? Current was proportional to W or L, assuming everything else same. So width and length. If you keep the width and length of PMOS and NMOS exactly same, you will end up something like this, where PMOS has offered more resistance, so it will have more transition time, and eventually you will have more delay. So what they typically do is, in order to make their resistance equal, you make PMOS wider than NMOS and keep the resistance length same. That will make more current. That will equate, I would say, overall the current and the resistance by making PMOS much wider. Some of the technology parameters that I've used, K dash, will be different for PMOS, and that they make the PMOS current slower. Got it? So we covered this one, we covered this one, and we covered this one. Okay, we didn't cover this thing. So if you want to calculate overall propagation delay through somebody asked the propagation delay of the inverter, Then you take an average of the NMOS value and the PMOS value, and then average, and that will be it. But I think if you do initially for hand calculation, that's okay. So now the second thing is, so we covered the definition of transition time, delays, this. Now question is, how you can reduce the delay and reduce the transition time. I mentioned that in the last video too, that you can do that by reducing R and C. But then question is, okay, how can I reduce R? As a designer, what things are in my control to reduce R and C's? Let's look into resistance. If you remember one of the previous videos, I didn't derive full equation for on resistance, but I came up with this R is equal to V over I. So V is really VDD, like maximum voltage we can reach a supply voltage. Sometimes I write VD, sometimes VDD, forgive me for that, but it's the same thing. And current underneath is proportional to width over L, VGS minus VT, and this is the linear region I'm talking about. So with this equation, as I said, the benefit of equations is you can find some relationship. So if I want to reduce resistance, what can I do? I can reduce supply voltage, which will also, keep in mind, when reducing supply voltage will have another effect, that when you reduce supply voltage, this thing will get smaller. So when this gets smaller, what happens is this will get higher. So there are two impacts of this one with supply voltage. And if you increase width of the transistor, you use bigger transistors, a bigger drive strength cells. If we're talking about standard cells, and we'll touch on standard cells, then you will have low resistance. So typically when you pick different AND or NOR inverter, you say, okay, I need a high drive strength because their resistance is low. And as a result, their delay is low. So depends on which parameter you vary and which thing will swing more. And even if you think of resistance as a basic formula that we have, okay, that it is, I mean, if it's a wire, I will touch a wire, but yeah, I put the formula as a wire resistivity, the basic core property of that conductor, and it is multiplied by length of that wire and over the width of that wire. So wider the wire, it will have less resistance. Longer the wire, it will have higher resistance. Same case for transistor. Longer the channel length, higher the resistance. This goes up. So you understand these 3-4 parameters for resistance. So for capacitance, what are the parameters for capacitance? So capacitance basic definition is always in epsilon over T. This is the property of the material. Now what kind of material? Some material will have higher capacitance. In transistor we use silicon dioxide. And this is the thickness of the spacing. So our capacitor is this. And this is the dielectric. This is the property of this, and this thing is how wide is it. So if your thickness is wide, okay, your capacitance is low. So in this case, if this is wider, capacitance will be small. So you need to make this thing wider. And you need to make these guys acting as a dielectric, you need to make these wider. They will have some other effects to which we will talk in future videos. So if you want to decrease capacitance, you need to make a dielectric bigger. You need to use a material with low capacitance, and your width will need to be smaller. So here you have a factor fighting with each other. If you make your width wider, it's good for resistance, But a wider width will give you low resistance, but it will also give you high capacitance. Okay, so you need to see different variants. That's why you need to have a standard library so that tool can pick different different cells for it to adjust the delay appropriately. And similarly, resistance, higher resistance, sorry, length. This is for the conductor I pick, which O means overall area, W multiply L. So if this diffusion, remember this yellow thing which is behind the pink thing, this overall thing is smaller area. It will have less capacitance. This overall area, this two, is from here, this whole thing. This is width and this is length. In this case, not length of channel, length of the diffusion area. If the whole area of this thing is smaller, it will be less capacitance. So those cells which are bigger and bigger to have a smaller delay, in those cases, their capacitance will increase. And sometimes we see what is the dominant factor on it. Its dominant factor is, W increases, also increases current. So current effect tends to increase, or the capacitance becomes a problem. So you need to think of those. But again, as a physical design people, in the digital flow, we are not doing hand calculation, and I'll show you tools calculate all that, and tools pick the cells that we need. But it's important to understand the impact of different parameters when you want to play with delay. Same thing for transition time, is same R on and CL. So it's the same discussion that I did here holds for transition time. Okay, I really hope, sorry for a longer video, but I really hope that I'm able to convey the key concept that I wanted to explain. Any questions? Let me know, please. Thank you so much. Bye.